Hey everyone, welcome back to my channel Beaker and the Board. So today's class is the last one for this chapter, Redox Reactions, and your class is entirely based on redox titrations. So before heading on to redox titrations, you need to know what are titrations. Titration is the process by which you determine the strength, you determine the concentration of one solution with another solution whose concentration is already known to you. That means here in this titration process, you will be provided with two types of solution. There are two solutions in titration process. Solution 1, say for example, suppose solution 1 concentration is not known to you. Solution 1 with unknown concentration. Solution 1 with unknown concentration, whose molarity, whose strength is not known to you. That will be called an analyte. That will be called an analyte, or it is also called the titrate. It is also called the titrate. And the solution 2, whose concentration is already known to you. Known concentration. Solution 2, whose concentration is known to you, molarity is known to you, that will be called a titrant. So that means whenever you do titrations, whatever kind of titration it is, you will be provided with two solutions. One solution whose concentration is known to you and the other solution whose concentration is not known. So the solution 1 whose concentration is not known, which is unknown, that will be called analyte, and that is taken in the conical flask. In the conical flask, you take the analyte or you take the titrate. And the solution whose concentration is already known to you, that is taken in the burette. That is taken in the burette. That means the titrant is taken in the burette, whereas the analyte is taken in the conical flask. So titration is basically quantitative analysis. Quantitative means determining the quantity, determining the amount, determining the strength, the molarity of an unknown solution using another solution whose concentration is known to you. Now, the next topic is that what are the types of titrations? There are mainly two types of titration. One is the non-redox titration. Non-redox, that means in this kind of titration, there is no change in the oxidation number. That means whenever you do this kind of titration, there is no change in the oxidation state or oxidation number of the species of the atoms involved. Now, what are the types of non-redox titrations? Non-redox titrations are of three types mainly. One is the acid-base titration. For example, you must have done this using sodium hydroxide, hydrochloric acid, using methyl orange or phenolphthalein as indicator, right? NaOH, sodium hydroxide, HCl, producing sodium chloride and water. And for this purpose, what do you use? You use methyl orange, or you can also use phenolphthalein as the indicator. They are the indicators. Why are indicators used? I am coming to that afterwards. So acid-base titration is a kind of non-redox titration. If you find out, you will see that none of the atoms are changing their oxidation state. All the atoms are having the same oxidation state during the reaction, before the reaction, and after the reaction. There is no change in the oxidation state. The next one is complexometric titration. Complexometric titration using EDTA and all that. It is not in your syllabus right now. Just know the type of titrations that are non-redox. So non-redox titrations, acid-base titration, which you will be doing in your lab. The next one is complexometric titration. Another type is the precipitation titration. Precipitation. That means obviously precipitation reactions are double displacement reactions, right? And I have already taught you, you can consult my previous class where I have explained that why double displacement reactions are not redox in nature. No double displacement reactions are redox. All the double displacement reactions, that is neutralization reaction, precipitation reactions, they are non-redox in nature. There is no change in the oxidation state. So that means non-redox titrations which involve no change in the oxidation state of the atoms. There are three types, that is acid-base titration, complexometric titration, and the precipitation titration. The next thing of discussion is the redox titration. Redox titrations are those which obviously will involve change in the oxidation state, which will involve change in oxidation state, and you will do this kind of titrations in your practicals. Change in the oxidation state. For example, if I tell you the titration of potassium permanganate, and oxalic acid, titration of potassium permanganate with oxalic acid, producing carbon dioxide, obviously in the acidic medium is required in presence of H+, producing carbon dioxide gas, Mn+2 ion, and water. If you find out the oxidation state, you will find that every species is changing their oxidation number. For example, manganese from +7, it is changing to +2. That means reduction. In oxalic acid, each carbon is having a +3 oxidation state. In carbon dioxide, carbon is in +4 oxidation state. That means this titration of KMnO4 with oxalic acid is a redox titration, because potassium permanganate is reducing itself, is getting reduced to Mn+2 ion, and oxalic acid, where carbon is in +3 state, is getting oxidized to +4. Now the next point is when to understand that the titration is completed. When will you understand that the titration is done? That is by the equivalence point. Now what is the equivalence point? Equivalence point is also called the end point of the titration. That means you need to close the cork, you need to stop the titration, you need to close the burette. What is that? At the end point or at the equivalence point, the number of equivalence of the titrant, that means the known solution, the solution whose concentration is known to you, is equal to the number of equivalence of titrate or the analyte. Now you may think that how to understand that the titration has been completed. That is by seeing the change in the color of the indicator. As I said that I'll be discussing right now. In this titration, in this redox titration, KMnO4 itself functions as the indicator. You don't need to add any indicator from outside. KMnO4 has two kinds of functions here. Potassium permanganate acts as the oxidizing agent, as well as it functions as the self-indicator. KMnO4 functions as the self-indicator. That means in this titration, what happens when you start pouring? I'll be sharing the picture with you once again. Let me share the picture once. Just write it down. Equivalence point is that in which the number of equivalence of the titrant is equal to the number of equivalents of the titrate unknown solution. That means now you know what is the equation for normality. Normality is equal to the number of gram equivalents of the solute, number of gram equivalents of the solute divided by volume of the solution. That is how we define normality, right? So normality means N is equal to number of equivalents NE divided by volume. That means when number of equivalents of the titrant is equal to the number of equivalents of the analyte or the titrate, that is when the end point is achieved. This is the end point. Both of them, that means KMnO4 and oxalic acid, will have the same number of equivalents. So how do you, that means the equation becomes, for calculation of the other part, what will you do? N1 V1 is equal to N2 V2. Because see this NE titrant, number of equivalent of the titrant, is equal to the number of equivalents of the analyte. That means N1 is the normality of analyte, normality of titrant. N2 is the N2, just a minute. N2 comes out to be the normality of analyte. Normality of analyte. Now V1 is the volume of the titrant. Volume of titrant, the reading which you get from the burette. Volume of the titrant, reading of the burette. When you do the titration, you get this from the burette reading. And V2 is the volume of the analyte. Volume of analyte. That means whatever volume you have pipetted out, that you pipette out. Suppose if you take 20 ml or 25 ml of the analyte. I'll discuss it once again. So your equation is this. Whenever you are asked to calculate N2, normality of the unknown solution. So N1 V1 equal to N2 V2. This is the equation. These equations you need to remember. So if you modify this equation, it becomes M1, just a minute, M1 V1 by M2 V2 is equal to N1 by N2. This is the equation if you convert the normality equation to molarity equation, because most of the times this equation is needed. So N1 becomes the number of moles of titrant, and N2 is the number of moles of analyte. So that means, how do you get this N1 and N2? Both N1 and N2 are obtained from the balanced equation. When you write the balanced equation for any redox reaction, you get N1 and N2 from there. Now see, this is the diagram. What is taken? Whenever you do titration, whatever titration you may be doing, whether it is non-redox or redox, you need to use this kind of setup. What is used? You need to use a conical flask. And what is taken there? In the conical flask, we take the analyte whose concentration is unknown. N2 or M2 is not known to us. We have to find out that. And in the burette, the long stand is the long pipe-like structure is called the burette. In the burette, we take the titrant whose concentration, whose normality or whose molarity is known to us. Say suppose for example it is 0.2 normal. 0.2 normal. Suppose for example. Now what happens? In the burette, we have taken KMnO4, potassium permanganate. Now what happens? Slowly the knob is turned on. The knob is turned on. In the conical flask, I have taken analyte. Say for example, I have taken oxalic acid. In the conical flask, suppose I have taken oxalic acid, whose concentration is not known to us. Suppose I have taken 20 ml of oxalic acid. How do you know it is 20 ml? Because you pipette that out. Pipette is another instrument. You pipette out the oxalic acid. Suppose you have taken 20 ml of it. So what happens as soon as you turn the knob on? When you turn the knob on, slowly and gradually, the drops of KMnO4 falls into the conical flask. Drops of KMnO4 falls into the conical flask, and you start shaking it. You go on shaking it, and after some time, the analyte becomes pale pink in color. This analyte, that means the analyte becomes pale pink. It should not be dark pink, it will be pale pink. The solution which was initially colorless, the analyte which was initially colorless, turns out to be pale pink in color. This is the stage where the end point is achieved, when the analyte slowly becomes pink in color, pale pink, and it does not disappear. The pale pink will remain, it will not disappear. That is the point of equivalence, that is the end point. And suppose at 26.7 ml, that means when you have poured 26.7 ml of KMnO4, the equivalence point is achieved. That means V1 is 26.7 ml, V2 is 20 ml, that which you have pipetted out. You have taken 20 ml. N1, that means KMnO4, is suppose 0.2 normal, and N2 you need to find out. So that means you need to find out using the equation that I have talked to you. So this is the entire thing about titration, about redox titration. Next, I have discussed some numericals regarding this formula, regarding this concept. Go through them and understand the concept. Okay, so after the discussion of redox titration, this is your first question. Read the question and understand. Your question is how much in gram you have to find out the weight, amount of ferrous sulfate that can be reduced by 52.68 ml solution of 0.05 molar KMnO4 in acidic medium. So obviously before solving any sums regarding the equivalent weight or the redox titration, you need to write the balanced equation first. So it comes out to be something like this. Okay, so for the question, the balanced reaction is something like MnO4 minus, because we are using permanganate. So MnO4 minus plus 5 ferrous Fe2 plus 8H plus arrow Mn plus 2 Mn plus 2 plus Fe3 plus it's 5 Fe3 plus 4H2O. So this is the balanced reaction for the sum that is given to you. So what can you see? That 1 mole of permanganate, 1 mole of permanganate is equivalent to 5 moles of ferrous sulfate, Fe2 plus in the form of ferrous sulfate, right? 1 mole of potassium permanganate is equivalent to 5 moles of the ferrous sulfate, which is from the balanced equation. So whenever you solve this kind of sums, you need to write the balanced equation first. So what can you say now? We know what is molarity. M is equal to N by V, right? This is how we write. That means we can say molarity is equal to the number of moles of the solute divided by volume of solution in liter. You must have read this in mole concept chapter, right? So molarity is equal to number of moles by volume of solution in liters. So we can also say, if I want to write 1 molar, suppose if I want to write 1 molar, what will I write? I must write like this: 1 molar is equal to 1 mole by 1 liter. Right? 1 molar is equal to 1 molarity is equal to 1 mole by 1 liter. Or we can also say 1 mole by 1000 milliliter. Right? So just I will modify this in the form of statement. So what is the thing? 1 mole of KMnO4, 1000 ml, 1 molar, 1000 ml, 1 molar of potassium permanganate is equivalent to 5 moles of ferrous sulfate. Why did I write in this way? Because this whole thing, 1000 ml 1 molar means 1 mole. 1000 ml 1 molar means 1 mole. So what can we solve in this way? So the equation next it comes to be, if I convert this moles to gram, what is the molar mass of ferrous sulfate? The molar mass of ferrous sulfate, if you calculate it, molar mass of ferrous sulfate is, for iron it is 55.5, so let's consider this as 56, plus sulfur 32 and oxygen is 16 into 4. So if you solve this, it is around, just solve it, it's around 152 gram per mole. 152 gram per mole, which we also say as 1 mole ferrous sulfate is equal to 152 gram, right? That means 5 moles ferrous sulfate means 5 into 152 gram ferrous sulfate, right? That means we can write the statement as 1000 ml 1 molar KMnO4 is equivalent to 5 into 152 gram ferrous sulfate. Right? Now what happens? What is given in the question? 52.68 ml and 0.05 molar KMnO4. So if you just modify it, simplify it, 1 ml 1 molar KMnO4. What does this mean? 5 into 152 divided by 1000 gram ferrous sulfate. 1000 gram of ferrous sulfate. So what is provided to us? According to the question, we are provided with 52.68 ml. 52.68 ml of KMnO4 is given to us. 68 ml. And what is the molarity? It is 0.05 molar KMnO4. That means if 1000 ml 1 molar KMnO4 oxidizes 5 into 152 gram of ferrous sulfate, then how much ferrous sulfate will be oxidized by 52.68 in ml and 0.05 molar KMnO4? Understood? So the question answer becomes something like this. 5 into 152 by 1000 into 52.68 into 0.05. If you solve the sum, the answer comes out to be something like 5 into 152 into 52.68 into 0.05 divided by 1000. So the answer is, I am giving you some time, the answer comes out to be 2.001. So it's 2 gram, approximately 2 gram. So I hope you have understood the question. The question is all about that a reaction is given to you. The question is asked that if we use potassium permanganate, if potassium permanganate is used to oxidize ferrous sulfate, potassium permanganate is used to oxidize ferrous sulfate. So it is asked that if 52.68 ml and 0.05 molar KMnO4 is given to you, how much ferrous sulfate will be oxidized? This is what is asked to you. So that means for solving the sum, any sum related to equivalent weight calculation or redox titration, you have to write the balanced equation first. What do you see from the balanced equation? That for 1 molar KMnO4, for 1 mole KMnO4, 5 moles ferrous sulfate is oxidized. From 1 mole, see the question, 1 mole of permanganate oxidizes 5 moles of ferrous sulfate. So what happens? Question is given to you that if a particular amount and particular volume is given, 52.68 ml and 0.05 molar KMnO4 is given to you, then how much ferrous sulfate will be oxidized? That is the question. So your question is how much ferrous sulfate will be oxidized if 52.68 milliliter 0.05 molar KMnO4 solution is provided to you. So what does it mean? 1 mole KMnO4 oxidizes 5 moles ferrous sulfate. Or 1 mole can also be written as 1000 milliliter 1 molar, because molarity is equal to N by V, number of moles by volume. If I say 1 molar means 1 mole by 1 liter, or we can say 1 mole in 1000 ml. That means you can also write this as 1000 ml 1 molar is equal to 1 mole. 1 molar is 1 molarity. It is the concentration unit. That means 1000 ml 1 molar KMnO4 oxidizes 5 moles of ferrous sulfate. Since the question is asked to calculate the amount, you are asked to calculate the weight. That is why I have converted the moles to gram. 5 moles of ferrous sulfate means if 1 mole is 152, then 5 moles means what? 5 into 152. So what happens after that? 1 mole ferrous sulfate is 152. That means 1000 ml 1 molar. 1000 ml 1 molar, which we say as 1 mole KMnO4 oxidizes 5 into 152 gram ferrous sulfate. That means if 1 milliliter is given, then how? Just use the unitary method. The answer is achieved. So just if you use the unitary method, you will get the answer. 2 gram. That means your correct option is option C. Option C is the correct answer for the given question. Option C. Okay. Now your next question is something like this. It is almost similar to the first question. Almost 99% similar. But the thing is, the previous question you were asked to calculate for ferrous sulfate. But this question is about only ferrous ion, Fe2 plus ion. So read the question first. The question is given the amount of Fe2 plus ions that can be oxidized by 1 ml solution of 0.1 molar K2Cr2O7 in acidic medium. So what is asked to you? You have to calculate the weight of Fe2 plus ion. You have to calculate the amount of Fe2 plus ion. What amount? The amount that is oxidized by 1 ml solution, 1 milliliter solution of potassium dichromate. What is the concentration of that? 0.1 molar. So again, for that you need to write the balanced equation. I hope you have understood the question. The question is given potassium dichromate in acidic medium oxidizes ferrous ion Fe2 plus ion to ferric. The question is given how much ferrous will be oxidized. How much ferrous will be oxidized if 1 milliliter solution 0.1 molar K2Cr2O7 is used. A particular amount, particular concentration, particular volume of potassium dichromate is said. From that you need to find out how much ferrous ion will be oxidized from the given amount of K2Cr2O7. Now let's start solving the sum. Okay. Now, so obviously you need to write the balanced equation again, and the balanced equations is something like this. Cr2O7 2 minus dichromate ion with 6 Fe2 plus 6 ferrous ion with 14 H plus gives 6 ferric ion plus 2 chromium plus 3 and 7 H2O. If you want to know how the reaction is balanced, you can consult my previous video where I have taught you how to balance reaction by ion electron method both in acidic and basic medium. So let's start the sum now. So what do you get? That means again from this sum we get that 1 mole dichromate, 1 mole of dichromate Cr2O7 2 minus is equivalent to 6 moles of Fe2 plus just from the balanced equation. Or we can also write again the same thing, 1000 milliliter 1 molar potassium dichromate or dichromate ion is equivalent to 6 moles of Fe2 plus. Since you are asked to calculate the amount, the weight, so you need to convert that moles to the gram. You have to convert the moles to the gram. What is the gram atomic weight of iron? The gram atomic weight of iron is 55.55 gram. 55.55 gram or 55.55 if you say it is gram per mole, which means 1 mole of Fe, or you can say or Fe2 plus. Does the charge affect the molar mass? It doesn't. The charge Fe and Fe2 plus, even Fe3 plus, they will have the same weight. The charge, the oxidation state does not affect the molar mass. So that means 1 mole of Fe or Fe2 plus is 55.5 gram. Right? So if you modify the statement, it becomes 1000 ml 1 molar potassium dichromate or dichromate ion is equivalent to, I am just converting the moles to the weight, 6 into 55.5 gram of Fe2 plus. Just use it from the balanced equation. Now what is given to you? The question is given if you are provided with 1 milliliter and 0.1 molar dichromate, then how much iron, how much Fe2 plus will be oxidized? For 1 mole it is 6 into 55.55. But if it is 1 molar, 0.1 molar and 1 milliliter, then how much Fe2 plus will be oxidized? So the answer comes to be like this: 6 into 55.5, obviously divide by 1000 first, into 1 into 0.1 gram of Fe2 plus. So if you solve this sum, I am giving you some time, solve the sum. It is 6 into 55.5 into 0.1 into 1. You don't have to take the 1 though. Divided by 1000. That means it is 0.033 gram Fe2 plus. That means if you are provided 1 milliliter and 0.1 molar potassium dichromate, then you can oxidize 0.033 gram ferrous iron. So what does the statement infer? What can you infer from this? What can you conclude from this? 1 milliliter 0.1 molar potassium dichromate as given in the question can oxidize 0.033 gram Fe2 plus iron. As I said, it is just the similar as the previous sum. But one slight difference: in the previous sum it was asked for the entire ferrous sulfate, and this sum is only for Fe2 plus iron. That's it. Let's move to the next sum now. Okay, so this sum is about, see the reaction it is given, S2O3 2 minus. This is thiosulfate. This is thiosulfate. Thiosulfate with permanganate ion in aqueous medium producing manganese dioxide MnO2 plus sulfate and hydroxide. So you are asked to calculate what volume of 0.1 molar KMnO4 solution is required to react with 0.158 gram of sodium thiosulfate according to the above reaction. That means the previous two sums were about the calculation of weight, but this sum is about calculation of volume. Volume of what? Volume of potassium permanganate, whose concentration is, whose molarity is 0.1 molar. Why is it required? That volume of X volume, X ml of 0.1 molar KMnO4 to react with 0.158 gram of sodium thiosulfate. You need to find out the volume of potassium permanganate that is required to react with 0.158 gram of sodium thiosulfate. So for that again you need to write the balanced reaction. The reaction is given, it is not balanced, you need to balance it first. So let's solve the sum. Okay, so let's start the sum now. The question is given, you need to balance it. The balanced reaction is something like this: 3 moles of the thiosulfate reacting with 8 moles of permanganate plus H2O gives 8 MnO2 plus 6 SO4 2 minus plus 2 OH minus. This is the overall balanced reaction. What can you see from this? That 8 moles of permanganate, 8 moles of permanganate is equivalent to 3 moles of thiosulfate, 3 moles of the thiosulfate. Or we can say 1 mole, if 8 moles is 3 moles, then 1 mole of permanganate will be equivalent to 3 by 8 moles of thiosulfate ion. Thiosulfate ion. Or we can also say 1000 ml, as we know 1000 ml, 1 molar permanganate is equivalent to 3 by 8 moles of thiosulfate. Right? Just as I have explained to you in the previous two sums. So what does it become? What is given to you? What volume of 0.1 molar? Let's consider this first 1000 ml only. 1000 ml, 0.1 molar permanganate. How many moles would that make sodium thiosulfate? If 1 molar permanganate in 1000 ml means 3 by 8 moles of thiosulfate, then 1000 ml 0.1 molar permanganate, what would that mean? It is 3 by 8 into 0.1 mole of sodium thiosulfate or thiosulfate ion. That which means it is 0.3 by 8, right? 0.3 by 8 moles of thiosulfate ion. Since the question is specifically given for sodium thiosulfate and potassium permanganate, we will use for sodium thiosulfate. Now, molar mass of sodium thiosulfate, how do you calculate it? It is equal to sodium, it is 23, so 23 into 2 plus sulfur is 32 into 2 and oxygen is 16, so 16 into 3. That would simply mean that it is 158 gram per mole. The molar mass of sodium thiosulfate is 158 gram per mole. That means 1000 ml 0.1 molar potassium permanganate is equivalent to 0.3 by 8. I am just converting it to weight because the question has been given with respect to the weight. You have to calculate the volume for a specific amount of sodium thiosulfate. So it is given 0.158 gram. The sodium thiosulfate amount is specifically given. So since the weight is given, so I am converting the moles to the gram. So it is 0.3 by 8 into 158. If you solve this, it comes to be something like 0.3 by 8 into 158. So it is 5.95 gram. 5.95 gram. That means 1000 ml 0.1 molar KMnO4 reacts with 5.95 gram sodium thiosulfate. 5.95 gram of sodium thiosulfate. However, in the question it is not given 1000 ml. The concentration is given 0.1 molar, but the volume is not given. If it is 1000 ml 0.1 molar KMnO4, then it reacts with 5.95 gram sodium thiosulfate. You have to find out the volume of KMnO4 now. It is not 1000 ml. We have calculated with respect to 1000 ml. That means, so 1000 ml 0.1 molar KMnO4 reacts with 5.95 gram sodium thiosulfate. Now that means, or we can invert the statement, just round it off. Since we are asked to calculate the volume, whatever we calculate, we keep it on the right hand side. We can say 5.95 gram sodium thiosulfate reacts with 1000 ml 0.1 molar KMnO4. Don't change the strength, don't change the concentration. Concentration is given as 0.1. That means 1 gram sodium thiosulfate reacts with how much? 1000 by 5.95 ml 0.1 molar KMnO4. A specific amount is given. What is the specific amount? The specific amount is 0.158. 0.158 gram sodium thiosulfate reacts with 1000 by 5.95 into 0.158 gram, not gram, sorry, 0.158 milliliter of 0.1 molar KMnO4. If you solve the sum, it comes out to be something like, just a minute, it's 1000 by, just a minute, so it is 1000 divided by 5.925 into 0.158. It is 26.6 ml of 0.1 molar KMnO4. So according to the question, what is given to you? You have to find out the volume of KMnO4 whose concentration is 0.1 molar. That will react with 0.158 gram of sodium thiosulfate. So what do we do? That means if you write the entire statement in this way, therefore 26.6 ml KMnO4 26.6 ml 0.1 molar KMnO4 reacts with 0.158 gram sodium thiosulfate. With this sum, we come to the end of the chapter redox reactions. My next topic of discussion will be organic chemistry, where I will show you balancing, where I will show you the IUPAC nomenclature. I will teach you how to write the IUPAC nomenclature of different organic compounds. Stay tuned for my next class. If you like the video, like, share and subscribe. Thank you everyone.